would like to thank the organizers for the opportunity for talking about this work of ours. Yes, this is a big title. A shorter title is like this. From disorder to order and disorder again. There are many disorders in this work and this field, and people make confusion of what type of disorder is that. So I try to clarify the meaning of disorder. For instance, this disorder here has nothing to do with this disorder. So let me start thanking my collaborators, which is Eric Andrade. He is a colleague in São Carlos, and Matthias and Stefan, which are in Dresden. Matthias now moved to somewhere in Australia, I think it's Melbourne. And the financial support by CNPq and FAPESP. So the outline of this talk, well, I have to talk about the model that we have. So it's supposed to be a good model for this compound here, the Erbium titanate. And I will review what's known about these compounds. So I have to talk about what's the mechanism of order by disorder that you know very well. It was already introduced in the first talk of this workshop by Santiago, which unfortunately is not here. Oh, picture. Do you want a selfie? Okay, you took it? Oh, stiffness there. But the mechanism for the order by disorder is different origins. It can be either by thermal or quantum origin, or either by structural origin. And both of them are called disorder, but they are not. They are different, fundamentally different, and I will review about that. And then I will talk about our proposal of understanding what happens when you dope the Erbium titanate with some non-magnetic impurities. And I will try to convince you that the physics of this material is a random field physics as opposed with random mass physics. And I suppose it to be clear by then what I'm meaning and arrive then. And then our proposed scenario of a glassy phase, which are supported by Monte Carlo simulations, and then flesh out diagrams and perspective conclusions. So if you want to interrupt me any time for questions, be welcome. So the model is these rare earth titanates, which are in these FCC lattice of corner sharing tetrahedra. Our main character here, our main actor is the erbium, which is a magnet, and the titanium and oxygen are responsible for the lattice. So many interesting physics happens in these rare earth titanates, like spin ice, which was already talked about here, and maybe proposal of spin liquid and spin ice. But today, I'll be focused on this erbium titanate, which displays the order by disorder mechanism. And the key features about this compound is that it's a multi-insulator, but with a strong crystal field and spin-orbit coupling. And after you do the math, you end up in an effective model for this compound, which is an easy plane XY model with off-diagonal interaction. So instead of only XX, there is also XY interaction. Is there a question? Yeah. XY plane, yeah. Yeah, next slide. Here. So yeah, it's amazing how people could come up with this model, because each site has its own local XY plane, and the Z-axis, the local Z-axis are pointing out of the tetrahedra. Actually, people can even compute the exchange couplings, which is very low. So There are phase transitions for paramagnet happens at very low temperature. And due to spin-orbit coupling, these exchange couplings here are not so easy in the sense that they depend on which pair you are looking at. For instance, you have this cosine phi ij, meaning that the interaction between this spin here 0 and 1 is different from the interaction from 0 to 3 and 0 to 2. So you have to be careful with this parameterization. We are, we are not talking about any dipole interactions here. Hopefully, much weaker. And we don't need any. Well, that's always a question that you can ask, but we don't need that to explain the experiments so far. So you can rewrite that Hamiltonian in terms of this parameter alpha, that is the ratio between these exchange couplings, and they appear here, here, and there. And this parameter is of order 0.6 for the Erbium titanate, and that's the number that I will be using from now on. So last slide for reviewing the model. Highly frustrated model. Usually we think about the geometric frustration. Yes, it's a frustrated lattice, but we don't even need to close the triangle to see the frustration. For instance, if you look at the interactions between spins site 0, the spins at site 0 and 2, it wants to align in the x axis, like this green one here, which is the local x-axis of site 0. And but the interaction with the other spin 1 here want to align in the y direction. So these spins in the middle here doesn't know what to do. So this is frustration, and that's why we call this system to be highly frustrated. The frustration is due to spin-orbit coupling, not to not to the geometry of the lattice. Although the geometry of the lattice also helps to be frustrated. Okay, now you go to the review of what's the mechanism of all body disorder. So I'll probably be fast here because many of you are familiar with that, but if not, please stop me. Let's start with the classical Hamiltonian. So if you get this Hamiltonian here and look for the ground state is parameterized in the Hamiltonian, and from alpha less than -2, all the spins want to point in the x around the x-axis, with 2 pointing in one direction, the other 2 points in the other direction. Of course, due to Z2 symmetry, you can flip around. Alpha greater than 2, they want to point in the y direction. But for alpha between -2 and 2, something very peculiar happens. The spin can point in any direction in the xy plane. Any angle theta here has the same energy, and this energy does not depend on alpha. That's something that happens a lot in highly frustrated systems. For instance, the J1, J2 model in a square lattice also has features like that. So this entire part of the phase diagram is highly degenerate. The ground state in any point here is massively degenerate with the spin pointing any direction in the xy, in the local xy plane. Well, the material is spin 1/2, but I'm talking about the classical spin S Hamiltonian. This is classical. I will put quantum fluctuations later on. But just to start, let's start easily. and consider the classical. So the Erbium titanate is here, it's around 0.6, as I told you before. There is this compound, platinum, whatever, that is a little bit off this degenerate region. I'll talk about it in the very end of the talk. And there are many other compounds that are in the other phase, but I didn't put here. Just to let you know that there are many interesting experiments in these systems. So okay, let's focus on the degenerate phase, where the ground state doesn't depend on parameter alpha and is massively degenerate. What happens is that although the ground state is massively degenerate, when you put temperature, some states are favored by this other mechanism. And one way of thinking on it is the following. Let's suppose that I look at this spin in the middle here. So our reference state is the one that is making an angle theta with the local x axis. And the molecular Weiss field is this H naught here, due to the interaction with all other spins. But of course, if I let thermal fluctuations, these guys will tilt a little bit due to thermal fluctuations, and these thermal fluctuations will give rise to a fluctuating field. And of course, this fluctuating field will make an angle with the Weiss molecular field. And we want to minimize free energy with this energy, the internal energy minus Ts. And we already minimized the internal energy. Now you have to maximize entropy. And to maximize entropy, we have to look for this angle gamma here to be perpendicular to the field. So this will tilt more the spin in the middle. So to increase the entropy, that's another way of seeing the order by this other mechanism. So I will try to maximize entropy and look for the angle theta here that makes gamma equal pi over 2. And if you look for it, you find that a few angles theta star fulfill this, which are 0 and 60 degree and 130 and so on. So as Santiago mentioned in his first talk at this workshop, if I look at if this is the ground state manifold, which is parameterized by theta, and I look at the density of state at low energies, this density of state has a peak at these angles. So when you put thermal fluctuations, this state will minimize the free energy, and they will be favored. If you think this explanation is too naive or too wave-handy, you can do that with full glory, meaning that you get your pyrochlore lattice of spins, let it fluctuate, spending Gaussian fluctuations, compute the effective Hamiltonian for this Gaussian fluctuation. You can diagonalize exactly because it's Gaussian. Then you compute the free energy and obtain the free energy as a function of theta. And you see that you minimize the free energy at some angles, the angles that I told you before. So the nice thing is that then you have a parabola, and then you want to freeze the angles in these magical, the spins in these magical angles, and you pay some energy to cross the barrier, which is proportional to the temperature. Of course, this is only true for small temperatures. So if I want to now describe this model, the action for that, you have the fluctuations that we are used to, couplings, and these quantum fluctuations that I will put in a moment about quantum fluctuations, but then have to add this term that selects the angles that we were talking. And if you do the math, this is the value of this lambda, the concavity of the parabola. So it's of order milli-electron volts for temperatures of order Kelvin. You can also have the same effect by quantum fluctuations, and now you have to do spin wave approximation. Then you get 4 modes because each unit cell has 4 spins. Spin fluctuation is also quadratic. You compute the ground state energy and minimize the ground state energy for theta. And you also get the same angles that you had before. So thermal fluctuations and quantum fluctuations, they are all together. And if you want to model the effective model for that Hamiltonian, would be something like that, with now the lambda quantum mechanics of order milli-electron volt as well. So for small temperatures, you forget about thermal fluctuations. Any questions so far? Okay, now about structure disorder, meaning that these white balls here are diluted sites. So the green arrow is just the local x axis. The yellow arrow are the actual spins, and the spins missing this site here and this site, for instance. So what happens now? Well, at the mean field level, for very diluted system, you can think as that you diminish a spin that's supposed to be here by 1 minus epsilon pi, where pi is the probability of finding a diluted site. The other way around. Yes. Yes, they are xy. But just put a vector here, so I don't put a vector with x and y. Yeah. No. In the real material, there is a z component, but it's much the coupling is much smaller than those that I showed you. So one way of thinking of dilution or structural disorder is that the spin is diminishing, is not fluctuating anymore, like doing fluctuation in the xy plane, but it's diminishing, right? If you have a site that's diluted, it shrinks to 0. But let's not say that's so drastic. Let's say that shrinks a little bit. So if you go throughout the lattice, the spins are doing like that, shrinking and becoming up, shrinking and becoming down. Then you can see that the fluctuations due to structural disorder must be perpendicular to the fluctuation of thermal and quantum disorder, right? Because the fluctuation is now in this direction instead of in the perpendicular direction. So what happens is now that the fluctuations are the angle, the fluctuating field due to structural disorder should be the same one as in the thermal or quantum case, but with pi over 2 difference. So I know what will happen now. Instead of selecting the angle 0, 60 degree, 120, I will select the one that's 90 and 60 degrees all the way up, all the way around. So that's the final result. Thermal quantum fluctuations likes to select these angles here, 0, 60, 120, and so on. And structure disorder likes 90, 90 plus 60, and 30 degrees, and so on. And this state here is called Psi2, and this state is called Psi3. Don't ask me why, but that's what people call it. And amazingly, the experimentalists, they are really good guys, they can distinguish this structure from this structure. I don't know how they do that. Of course, I know it's just a neutron scattering, but you have to be very clever on how you do that. You have to apply some fields, magnetic fields, to enhance the signal. They are clever on doing that. So that's the ground state phase diagram. If I have only structural fluctuations, I would favor Psi3 here and Psi2 in the other position, and Psi2 with quantum or thermal, and Psi3 there. So that's what is known of this field. So if I want to describe the model, now I have to put even lambda d, but since lambda d compete with thermal and quantum fluctuations, it appears with a minus sign. And this lambda d is of order 4.7x. X is the fraction of a diluted system. So if it's no dilution, x would be 0. And it's the same order. So what this gentleman here proposed was the following, that at 0 temperature, there will be a transition between the Psi2 and Psi3 phase, which will occur when these lambda q and lambda d are equal. And this would happen if you put the numbers at 7%. And so everybody was happy with that. So this proposed to happen for this compound here. And the experiments went there, the experimentalists went there and measured. Not only for the Erbium doped Abel titanate, but also to other pyrochlores that has some structural disorder where cobalt is replaced by calcium and strontium. So this compound would model some side dilution, while these two ones, the copper is already there, but calcium and strontium, they distort the lattice differently, so it would mimic a bond disorder. So all spins are there, but the coupling is very random in space. Anyways, it's just randomness. And the experiment doesn't find the Psi3 phase. They have this phase diagram here, which for small dilutions, they have the Psi2 state, the clean state, and about dilution, about 50%, they find something that they call mosaic of Psi2 and Psi3, where in the neutron scattering, they show peaks of either Psi2 phase or Psi3 phase. So they draw a cartoon like that you have Psi2 and Psi3 coexistence. Okay. So clearly, this is not in agreement with that. So for the clean case was all good. And of course, you have to do a better job, because this picture here is only for X. Remember, you're saying that the spins are going this direction, but this is too naive and should be correct only for a very small axis. X is dilution. So for large dilution, something else must happen. Yeah, sure. Yes, you have to. But yes, yes. This is the mean field. When you do the mean field, you already average over this order. And so okay. So this ends the review. I will start to present what I've done, and let's pause a little bit and work out this Hamiltonian here, which is very to all of you, and then I ask what's the relation of this Hamiltonian with the other Hamiltonian. And apparently there is nothing to do, but I'll try to convince you that has everything to do. And that's, I think it's our main advance in with this regard. So Ising Hamiltonian is the classical Ising Hamiltonian. There is no quantum here. And I have the ferromagnet coupling, J is positive, and I have a longitudinal field. But this longitudinal field has zero average and some dispersion. So it's called random field Ising model. People still study this model for purpose of a glassy phase. But I will ask you the following. Is a ferromagnetic state stable against this random field? Let's say t equals 0, ground state. At t equals 0, of course, if this h was 0, we would have a ferromagnetic state, either up or down. Let's say up. Okay. So let's turn on the field. So it has a small width, and then I ask you, is there a way to diminish the energy? Because of course the field is random, so some of the spins will be aligned with the field, because the field's up, let's say, but some of them will be misaligned, right? So let's say that in this region here, by chance, so here comes disorder, the true disorder, randomness. By chance, this region, all fields are pointing down. So of course, I can gain energy by pointing the spins down. I don't pay exchange energy because all the spins here will be aligned, so it's a ferromagnetic island. And then you ask, but how much energy do you gain? Of course, if all of them are aligned here, I will gain the energy of order of the volume. But that's not the case because of randomness. So I have to sum. If I sum out the local fields here, I'm doing what's called a random walk in field space. Some of them are up, some of them are down. Average will be 0, but there will be a dispersion of the fields, of the sum of these fields. And dispersion grows with the square root of how many steps you walked. So the dispersion will grow with square root of the volume of the region. So there will be regions that most of the fields are pointing down, regions that most pointing up, and I will gain this energy typically. Okay, so I will put a hole here. But of course, putting a hole here costs a domain wall energy, because the system is ferromagnetic, so this domain wall will cost some energy, because there are misaligned fields. So this will cost the area of the blob. And of course, if it is discrete symmetry, because only point up and down. But if it's continuous symmetry, it costs a little bit less, because then I can go up and then rotate very slowly down. So it goes with 1 power less in L. And then I have a criterion. That's the so-called Inhi-Ma criterion that were published a long time ago. Sorry I didn't put the reference here. So the Inhi-Ma tells you that if this energy here for large L is greater than the domain wall cost, of course I want to put domains which grows indefinitely and then the ferromagnetic phase will be destroyed. So the phase, long-range magnetic phase, is destroyed only by randomness. And this happens, okay, I know how they scale with L, I can do the math. And for d less than 2, you shouldn't expect any ferromagnetic phase. And d less than 4, any ferromagnetic phase in a continuous symmetric case. Okay, so that's the pause from the Abel titanate or the pyrochlores. I ask you, is there anything related to this problem to the other problem? Is there any relation? Because that's the key. For me, this is the most important slide in this talk. So if you think there is not a relation, let me flash out this new slide here, that what's happening when I have quantum fluctuations, thermal fluctuations, and structural fluctuations all the same. So locally, let's say that this is impurity sites. So the bulk want to be in one phase, site 2, and locally, the impurities will nucleate another phase, site 3, which, looking at the ground state, the classical ground state Hamiltonian, site 2 and site 3 has the same energy. They are degenerate ground states, as the up and down, which are degenerate. So what random field is doing here is picking up locally 2 ground states. So it's breaking the symmetry, the Z2 symmetry locally, right, between up and down. That's what the field is doing. Here, the impurity is doing the same thing. It's breaking the symmetry between site 2 and site 3. So it's the same physics, although seemingly totally unrelated. But then this gives us clue what's going on. Impurities are trying to destroy magnetic order, right? Then I ask you, what is the order parameter? Is discrete order parameter or continuous order parameter? If it's continuous order parameter, xy, then there should be any order below d equal 4, and the experiments are done in d equal 3. But discrete is d equal 2. So which is the symmetry of the order parameter? Well, because of the order by disorder mechanism, it's discrete, right? You have upside 2 and upside 3 only, which picks up angles 0, 60 degrees, and so on, and 30, 90, and 100 and whatever, and so on. So if you think that this all wave hand, and there is no math on that, okay, let's go to math. There is another way of seeing the same thing I was telling you. That's the Hamiltonian, right? So that's our random, what we call random off diagonal exchange. So let's go to our instability argument. The instability argument is the following. Suppose there is order. So S are pointing to some direction, and the X is XY. So N points in any direction, the XY direction. Doesn't matter which one. Then you compute the molecular field in a given site. The molecular field has the parallel field, which is that H naught in the very beginning, and this H perpendicular, which is like the delta H. And this H perpendicular, you see, oh, sorry, I forgot to tell you, the model has a different change now. Now you have to put epsilons here, and the epsilons are 1 if the spin is there, and 0 if the spin is not there, it's diluted. So epsilons are random variables, which takes the value 0 or 1, depending on if there is or there is not a dilution. So this field, the perpendicular field is proportional to epsilon. So if epsilons are all uniform, you sum of that, if suppose it's uniform. So epsilons are all equal 1, and when you sum these, you have sum of cosine and sum of theta in the thetahedron, which sums to 0 because of that angles that I showed in the very beginning of the Hamiltonian. But if there is some epsilons, there is some spins that are missing, this compensation does not happen anymore, and the perpendicular field is finite. On average, it's 0, because the impurities can be anywhere. But the correlation between these fields are not 0 and proportional to x, like the round-the-wall case. And then you ask yourself the transverse magnetization. The transverse magnetization, of course, is proportional to the transverse susceptibility. And the transverse susceptibility is the inverse of propagator. And there is that lambda Q thermal plus lambda QM plus lambda disorder. And that's the gap, proportional to the gap. Of course, the transverse magnetization is proportional to the transverse field, which averages 0. But you don't have to look at the transverse magnetization. You have to look at the fluctuations of the transverse magnetization. And the transverse fluctuations, they are proportional to lambda square, so it's proportional to x. And this is finite. Okay. Average over disorder. Distribution epsilons are with a probability 1 minus x, and 0 with probability x. X is the concentration of diluted dilutant. So it's binary distribution. So the average is taken with thanks for the question. So you see that if there was no gap, or there was no order by disorder selection, these would diverge, right? Because for d less than 4, which is in agreement with the Enhima criterion that was showed before. And for those who want, this is a Goldstone mode. But due to order by disorder, the Goldstone mode is gapped. So the gaps prevents the order to be going away. Because if it were 0, then the transverse fluctuations would diverge. If the transverse fluctuations diverge, you shouldn't have an order. So that's the instability criterion. It's a self-consistent play. I like it very, I find it very playful. You suppose there is an order and you show there is not. No, it's average over that. So it's already average. No, doesn't matter. I'm saying that I suppose there is a magnetic order, and that's an instability criterion, right? I'm supposing that there is a magnetic order, and this magnetic order, this order is irrelevant because, let's say, well, of course there is some side that are dilute, but if you cost grain, if you look at RG sense, magnetic order is uniform. And if it's uniform, you should have a Goldstone mode, and that's there. And then I look at, I consider perturbation due to disorder, which makes a transverse field. And this transverse field kills the order if there would not be a gap. But there is the gap, and the gap saves the order. Another way of thinking that is the following. Suppose what is the exchange field, the off-diagonal exchange doing here? Suppose you have order in the x direction. So you have a field in the y direction. That's how you kill the order, right? There is a order in x, but then you right away put a field in the y. So that's how you kill it. In the clean system, you don't kill it because you sum of all the angles, and this is 0. But when you dilute, there are some uncompensated fields, and there will be a net field in the perpendicular direction. So our proposal for phase diagram is the following. Let's suppose in the classical case. So suppose the classical case, let's go to quantum. Remember, there is that previous phase diagram that these people proposed. So psi 2 and psi 3, this is just perturbative mean field calculations, and they are here. But then if I increase this order, I would have a phase transition where I would not expect any disorder. When that happens, when S, the transverse fluctuation, I mean. When the transverse fluctuation is of order S, you kill the order. And this is local. It's a local criterion. If you do the math, you show that this is equivalent, that that field, the local field, the guy here, this guy is proportional to delta H square, which is this delta H. This is proportional to the gap, because this is delta H square and this gap square. So that's the criterion, that locally the disorder fluctuation is so strong that you kill the gap due to order by disorder. So disorder kills the gap that was originated by order by disorder. But this order by disorder is the quantum and thermal fluctuations, and disorder is structural disorder. So that's why I told you there are many disorders here. Well, nobody's laughing, so probably my joke was not good. So we propose, so what happens after this critical impurity value? Well, something that has to happen, and since you break the system into puddles of psi 2 and psi 3, this should be a glass. That's our proposal. And to show that this proposal has some support, Monte Carlo simulations. So Eric was the one that did the Monte Carlo simulations, and for small dilution, it seems that there is some features in the specific heat, but for dilutions a little bit greater, there's nothing. No cusp in the specific heat. So other parameter, and if you look at the associate correlation length, I'll cross at some point. Great, so things happening. But if you look at the magnetic correlation length, there is no crossing. So small systems seems to have a big, not big because it's divided by L, but some fraction of the system is in some phase. But when you increase L, you diminish that. It's because you are breaking those puddles. And you increase L, the puddles are the same size, but then you average more and more, and the magnetic order diminishes. Many different samples. It was for those numbers, for 12 was of order almost 100. For 6 it was 500, something like that. Yeah, that's the next step. We did all the scaling and the computer. Everything works fine. This is a glassy transition. Well, you can already see from here, right? Because this is a binder cumulant. Sure. Yeah, L is from 1 tetrahedron to the other is L equal 1. So there are lots of spins here. It's 1,000 spins. Mm-hmm. Yeah. I totally understand. Yeah, there are thousands of spins. In L equal 12, you hit the machine memory. So we can also compute the distribution of magnetization. So mx and my over the sample. So you sweep the sample and inquire where a given site, a given spin in the site is pointing to what direction. And you can see that for no dilution, zero disorder, most spins are pointing to those magic angles, which are the psi2 angles, 0, 60, whatever, and so on. And when you increase dilution, then you see that the other angles are more favored, so in the psi3 phase. But for higher dilution, there is no, so it's democracy. So they can be point anywhere, either psi2 or psi3. And in the experiment, they will say there will be puddles in psi2 and puddles in psi3, but that's not the precise picture that you should have. You can point anywhere. There are puddles, of course. Sure. Yeah, we compute the M6 as well. Well, I didn't put here, but yes, the M6 other parameter is just cosine cosine of this angle here, and we see that all works perfect. I just wanted to convince you the glassy phase here. So that's the signature of a glassy phase. You see that it's not shrinking to zero, meaning that there are puddles where spins are aligned. If they were not aligned, puddles that were not aligned, the radius should shrink to zero. That's the paramagnetic phase. So this is not a paramagnetic phase. So the phase diagram that we compute by Monte Carlo is like this one here, which seems to be very alike to that one that we proposed. Because the arrow bars are big, but we are proud with that. And I hope to have convinced you that there is a glassy phase, but let me put all of that in a little bit more broader perspective. So our mechanism is the following. When you have frustrated magnets, and you put side dilution, which doesn't break any symmetry of the Hamiltonian, except the translational symmetry. You'd think, oh, you didn't break any symmetry, so the physics shouldn't be random field physics, because random field breaks the symmetry of the other Hamiltonian. But due to order by disorder, there are some ground states that are selected, and the order by disorder selected these states. So when you put randomness, other states are selected. So within this manifold of degenerate structural disorder is breaking symmetry. So it's random field. So so for frustrated magnets, that's our claim that we have seen that emergent, let's not call emergent, but the mechanism for understanding the physics is random field physics, not random mass physics. And what else for instance, you can ask about other magnets, like this guy here, which is two-dimensional J1, to be spin liquid. But this person here, Steve White, Chernshev, and Zhu, they put disorder on that, and they found nothing, which they call a spin liquid. Disorder-induced mimicry of spin liquid. But what is this spin liquid that they found? Well, let's go to our case. We have a glassy system, right? But in dimension. In 2 dimension, you shouldn't expect any glass. If you believe on Parisi result that the lower critical dimension for a glassy phase is 2.5. So in dimension 2, you should melt the glass phase. So if you melt the glass phase, you don't have a Edward Anderson order. You don't have long-range order. So what order do you have? You don't have any other order. So this, that's why they call the disorder-induced spin liquid. So it is a spin liquid in some sense. A disorder spin liquid. Some other guys have been proposed something for the same compound, but in the lower density regime where perturbation theory can happen. So they call a valence bond glass, the low density. But let's not talk about that. I think there are some. It's not totally clear what they are doing. This paper here is corroborate what we are saying, and also these other guys. And the random field mechanism was also found in Ising frustrate magnets by these other gentlemen here. So these random field mechanisms seems to be permeating more frustrate magnets than only the pyrochlores that I was talking here. I give my conclusions. Oh, and that's what I already said. The order by this other quantum and thermal fluctuations compete with structural fluctuations. So this gives to a random field light physics, and you get a cluster glass phase. But the destruction of the order phase is due to the destruction of the local spin gap, because remember, you put the disorder locally that's so strong that kills locally the gap. So this is not restricted to other systems. For instance, we can go to this palladium, erbium, doped with Erbium. That is the Palmer choker. In the very beginning of the talk, I told you there was a guy that was in Palmer choker, which has nothing to do with order by disorder. But there is a gap there. But the gap is not due to local disorder, just because you minimize the phase in the Palmer choker. If we go fast here. Yeah. So you have a Palmer choker, and there is a gap because you break the symmetry in the y direction. And if you put the numbers that we got in our theory, we would say that that local gap will be destroyed by only 4% of dilution. And this has to be checked experimentally. So with that, well, it was published in this paper if you wish for more results and for more details. And I thank you for your attention.